Imagine an agent learning to play a game. It can learn in one of two very different ways. It might improve the exact strategy it's using right now, learning only from the moves it actually makes. Or it might act one way to explore while quietly learning about a completely different strategy, even reusing experience it gathered long ago. That single distinction, whether acting and learning share a policy, quietly shapes an algorithm's sample efficiency, its stability, and what data it's even allowed to touch. Let's dig in. So what is the actual distinction here? Let's set the two setups side by side and make it concrete. The first setup keeps acting and learning unified. The agent improves the very policy it uses to gather experience, so its data always reflects its current behavior. SURSA and PPO work exactly this way. It's simpler to reason about and generally more stable, because what it optimizes always matches what it's actually doing. The second setup splits them apart. The agent acts with one behavior policy, often exploratory or even old data pulled from a replay buffer, while learning about a separate target policy, often the greedy optimal one. Q-learning is the classic example, exploring freely yet learning the value of the greedy strategy. This split unlocks reusing old data but demands real care. Here's a clean way to tell which camp an algorithm sits in. Walk the decision one step at a time. Start with the policy the agent uses to act, the behavior policy. This is what actually picks moves and generates the whole stream of experience. And it's usually a bit exploratory, so the agent keeps discovering fresh options along the way. Now ask which policy you're actually trying to improve, the target policy. This is the strategy whose value you want to learn and eventually deploy, and it's usually the greedy, optimal one you'd love to end up with. The entire distinction hinges on how this target relates to the behavior above it. If those two match, then acting and learning are one and the same, and you're on policy. The agent learns about exactly the behavior it performs, exploration included, which keeps everything consistent, but means it needs fresh data for every update. But if the target differs from the behavior, you're off policy. Now the agent can learn the optimal strategy while it explores and even replay old experience from a buffer, a huge efficiency win that comes with a distribution mismatch it has to correct. This is exactly what lets DeepQ networks reuse a giant replay memory instead of throwing every hard-won transition away. Boil it down, and three ideas capture the whole distinction. Acting and learning can share a single policy. That's on-policy learning, where the agent improves the very strategy it uses to explore, so its data always matches its current behavior, making it stable and simple to reason about, though it has to discard that data after every update. They can also come apart entirely. That's off-policy learning, where the agent behaves with one policy but learns the value of another, letting it pursue the optimal strategy while it safely explores something more adventurous. The payoff is reuse, and the price is mismatch. Off-policy methods can recycle old experience, learn from demonstrations, and even learn from logged human data for huge sample efficiency. But learning about one policy from another's data invites instability, corrected with tricks like importance sampling. All right, let's lock in the essentials. The distinction is about whether the policy an agent acts with matches the policy it's trying to learn, and that one choice shapes an algorithm's sample efficiency, stability, and reach. Methods that stay on policy, like SURSA and PPO, learn the very behavior they perform, staying stable but discarding their data after each policy update. The alternative, as Q-learning shows, learns a target policy while acting differently, so old experience can be reused and the optimum learned while exploring. That flexibility costs a distribution mismatch. The reason importance, sampling, and the infamous deadly triad exist. Want more reinforcement, learning demystified one idea at a time? That's exactly what we do over at Standarity.com. Come join us.